All right, great. Let's get started. Recording started. This is lab 10. This is your last lab of 281. So in 2 hours, you'll be done with lab. Congrats. Starting with announcements, lab 8 and 9 are due on the 19th, which is Friday. Lab 10 is due next Monday, and then project 4 is due next Thursday, I believe, the 22nd. No, the 22nd is Sunday. Your final is next Thursday. So just like the midterm, you'll have two options for final times, both 10:20 to 12:40, either the morning or the night. So hopefully one of those works well for everyone. Today we're going to do a little bit on generating permutations in place, and then we're going to talk about algorithm families, dynamic programming, and then we'll do the handwritten problem at the end. Lab 10 has a lot of content. I'll try to go slow and make sure to ask questions. I'll be looking at the chat if any arise. Before we start, let's review the last handwritten problem. Is graph cyclic? You're given an undirected connected graph, and we want to know if the graph contains a cycle. And you're given the graph in an adjacency list. So the two solutions that we would look for you to pick up based on the content of the lab were either a depth first search or a breadth first search. If we're looking at this depth first search solution, usually you do depth first search with a stack. This is done recursively, so with stack frames, you could say. I'll give you guys a little time to look at this. Essentially, you're going to start at any node U, and you'll first check to see if neighbor is not equal to parent for each neighbor of U. And if we've already seen that neighbor, then that means that we can return true because we've seen a node from two different paths, which is the same thing as having a cycle because we'll check every single path exhaustively. If not, then we just recursively call on each neighbor and add a stack frame for each neighbor call. With this solution, there are two bugs which cause seg faults. I don't think we need to wait for you guys to find all the bugs. It's kind of a little bit to trek through. The first one is we only want to perform a recursive call if neighbor is not equal to parent. So if we did this, where this if statement is outside of neighbor not equal to parent, then we'd get neighbor jumping to parent and then recursively calling back to neighbor, and we'd bounce back and forth and have stack frames forever. Second one is empty graphs don't have cycles, so we have to check for that in our rod function return statement. Moving on to breadth first search, it's generally the same algorithm. We're going to exhaustively check nodes and look to see if we've seen them before from a different path. The difference is for breadth first search, we're actually using a queue. We have some memory that we declared. Any questions on those two? All right, and then there's sort of a sneaky third solution, which is just to count edges. You know the graph is connected, so you know that there are at least n-1 edges. And you know that if there are more than n-1 edges, there's guaranteed to be a cycle somewhere. If you remember from 203, the pigeonhole principle, you know, once you place that n-1st edge, if you add any other edge, you're guaranteed to create a cycle somewhere. So the third solution would be count up every single edge, divide by 2 for the handshake theorem, and that should give you the actual number of edges out of that adjacency list. And then we can just check if it's greater than number vertices minus 1. All right, moving on to generating permutations, which will be important for project 4. So suppose you have this problem, you forgot your phone password. The first solution you think of is to try all n factorial combinations. N factorial is way too much to store for most n's that we're working with. We need to be able to enumerate every single permutation of those n items without storing all the combinations. Ideally, we do it in place, only storing n items. So let's look at permutations as being a tree. And we're trying to enumerate the entire solution space, the entire permutations of these 4 colors, let's say. So we have blue, yellow, red, and green. Starting from your root, you could start with blue, yellow, red, or green. Then from each of those colors, you can move to any of the next 3. What you get is that each of these leaf nodes, you could say, represent a path down that tree, which is in itself its own permutation. If you count these here, there should be 16. So, wait, 16, is that right? 24, right? 4 factorial. So, that means that we can represent a permutation using a depth-first search of the solution space tree. And if we remember, depth-first search goes as far down the tree as possible before recursing back. So what you'll get in a depth-first search of this tree is blue, yellow, red, green. And then you'll recurse back, green, red. Recurse back, red, yellow, green, etc. If we do that, then we will at some point have each possible permutation. Why depth first? This is a good question. Does anyone want to comment in chat? What do we think the maximum size of a stack versus a queue is in these search algorithms, where we're enumerating n factorial permutations? So we're going to have a maximum size of n for a stack, but a maximum size of n factorial for a queue. That's because at some point, a queue will hold all of these possibilities, whereas a stack will only traverse n levels down the tree and then recurse back. So therefore, we can use a depth-first search of that solution space tree to enumerate all of our permutations with a fixed amount of space. This is the pseudocode for generating permutations. If n fixed equals item.size, in other words, if all of the items are fixed, then now we can do something, process items, whatever that may be, whatever you're doing with the permutation. Otherwise, we need to permute all of the unfixed items. So we'll go through for each unfixed item from I equals n fixed to I is less than items.size. And for each item, we will swap that item into the last space, increment num fixed, and then recall gen perms. What that's saying is, let me add one of the remaining elements and then recall gen perms with one extra fixed element. Then every time we do that, we swap back, we revert the changes. N factorial for Q, or depth first search in this case, be similar to an in-order traversal, by the way. So I wouldn't say so. I would say they're somewhat separate ideas. N factorial for Q, because what a Q will look like is, first you'll have nothing in it. You'll add the root, and then you'll add all of its children. So from the root, you'll add 1, 2, 3, 4. And then from each of these 4, They'll be waiting in the queue. They'll all be popped down. All of their children will be added. Eventually, the queue will contain all of the leaf nodes, and the number of leaf nodes is n factorial. Are there any cases that we want to choose breadth first search over depth first search? Not in this case, not for permutations, but one huge thing to remember is breadth first search on an unweighted graph will always give you the shortest possible solution. We know the total amount of leaf nodes in this case is n factorial because we built this tree based on permuting each of these n colors. Could you explain why we need to revert after the recursive call? Yes. So if we're looking at this, we're going to swap the last item with another item, generate those permutations, then swap them back. The reason we do that is we want to constantly be maintaining the progress that we've made on the path we've had. So we need to swap back anytime we change something, because when a new branch gets called, or when new branch stack frames come back into the picture, then you'll want to continue from that branch. Does that make sense? If you didn't revert any changes, then different function calls of this function would be affected. Because at the end of the day, we're working on the same items vector passed by reference that every single one of these stack frames is using. Why doesn't it cause infinite recursion? Because every time you call gen perms another time where you're adding a fixed element, you're increasing the number of fixed. And if we get to num fixed equals items.size, then we'll do something and then return. So what this code is going to end up doing, which might be hard to wrap your brain around, is there's going to be almost n factorial calls to gen perms for each permutation. And then once we get to the end where we've gone all the way down this tree, we've generated 7 elements worth of permutations. Once we add that last one, now we have a new permutation. And every possible full-sized permutation of items will be the end of that tree. So most of the calls to gen perms are going to be just swapping items, calling it again, and swapping items back. And we're going to keep doing that and keep increasing the number of fixed items and having more and more stack frames until we finally have every item fixed. And we're going to have that happen n factorial times. Does that make sense? So maybe the next couple slides will also help. Gen perms is a procedure that will enumerate permutations of an input list. As you guys know, this is the list of permutations for 1, 2, 3, 4. This example might help you a little more with how the function works. If we have this list of 7 letters and we want to just look at the permutations that start with ACE, there are fewer. There are 4 factorial or 24 permutations rather than 720, because we've now eliminated the first 3 letters worth of permutation. So gen perms items n fixed is the call. If you call gen perms ACE BFGD, 3, it will enumerate these permutations because you've initialized this function call with 3 fixed. So you're starting on the branch that has ACE already. What we're doing in project 4 is we're going to call it with 1 item fixed because we want to try every single permutation. Came up from the gen perms above. It means it's not promising. We'll get to promising later. Isn't 7 factorial 50, 40? Possibly. There might be a mistake on the slides. But the point stands. Okay. Moving on. This is the same gen perms again. All right, algorithm families. We're going to cover a few relatively new ones. So we know about brute force. Brute force is trying everything naively, if I had to describe it simply. It guarantees optimality because you're guaranteed to see every single possible solution. It's very slow because you have to see every single possible solution. Greedy algorithm, we usually talk about being locally optimal. So given the information at hand, pick the optimal decision that might not be globally optimal, but it's still going to put you in the right direction. Usually greedy algorithms are fast and close to optimal, but they don't guarantee optimality. Divide and conquer, you can think merge sort. You'll break the problem into subproblems and then combine them. Backtracking is a constraint satisfaction problem. Satisfying constraints is not necessarily optimal, but given what you're checking, all you can say is that you will find some satisfying solution. So I know you guys talked about the n queens problem. N queens uses backtracking. You'll basically consider placing a queen on a space and then say, is this possible? Have I messed up yet? If you place a queen that can be taken by another queen, then you'll just recurse back and stop considering that branch entirely. Given that you're doing that, if you make it to the end, if you make it with n queens on the board, you've satisfied your constraint. There's not really a notion of optimality in that problem because a solution is a solution. But you may have problems where just satisfying a constraint doesn't guarantee that it's satisfied in the best way. Branch and bound is for optimization problems. Branch and bound is for optimality. And that's a very important thing to remember. It's probably the first basic question you might be asked on a final. Backtracking is a constraint satisfaction problem that guarantees a solution, but not necessarily the optimal solution. Branch and bound guarantees an optimal solution. The way it does that is it's still enumerating every permutation, but we're increasing efficiency by pruning branches. We'll stop considering a group of solutions that we know can't beat our current optimal solution, our current best solution, let's say. And last is dynamic programming. Save answers to overlapping subproblems. It's different than divide and conquer. We're building problems upon their constituent subproblems. And that greatly increases time complexity. What's the difference between, oh, yeah, there we go. So they both use subproblems. Remember how merge sort took, let's say, I think in the lab example, 8 items, and then recursively broke it into 4 and 4, 2, 2, 2 and 2, and then 8 singular solutions. And then we had a merge algorithm that merged those subproblems back together, essentially. In divide and conquer algorithms, there's no overlap. The problems aren't built upon each other. They're solved independently and then combined. In dynamic programming, you have this idea of remembering the simple solutions that you'll then use to create bigger solutions. Combine, yeah. Merge sort is, the conquer step is, in a sense, the combine step. If that makes sense. And there's definitely some semantics behind all of these. We won't give you any problem that we think can be argued against. I know binary search is technically not divide and conquer because it's like just divide. But we won't give you anything confusing. if you have a grasp on the general idea of these algorithm families, you should be able to see the solution to any problem we give you. So let's talk about branch and bound. Branch and bound is what you're doing in project 4. This is the branch and bound pseudocode. You're going to check a node. If it's not promising, return right away. What that means is if whatever algorithm you're using to decide if it could possibly be the optimal solution returns false, then you want to completely stop considering this branch on the recursion tree. Once it gets past that check, if it is a solution, then now we update our best solution. We're going to remember this one and then return. Past both of those, we're just going to continue checking each child U of our original V node. So we're going to recursively call on each child with the same best that we had. It might be weird to think of things as nodes. Much like how we were talking about generating permutations with a tree, a lot of times you can think about your progress towards a solution as a node. This is an illustration of pruning. If we took one step down the yellow path and called our promising function, whatever that may be defined as for this problem, and we found that it was impossible for any of these yellow solutions to beat blue, one of the blue solutions on a depth first search, then we're going to forget about it. And forgetting about it means returning here, so there are no recursive calls to any of these solutions. In practice, we're doing this with bounds. So for an optimization problem, we can determine when to prune by using a bound. Bound is an estimate of the potential of a solution space. So let's flesh that out. We'll have an upper bound, which is the best solution we've seen so far. So once we find a complete solution, and it is the best complete solution we have so far, that's the number we're remembering to compare possible solutions against. We'll also have a lower bound, optimistic estimate for remaining solutions in this branch. So we're looking for some way to quickly compute the best possible case for this branch, for the remaining solutions in this branch. Then what you'll do is take your current complete solution, you'll add the lower bound of an estimate for the remaining nodes. If that is still less optimal than what you've already found, forget about this branch. So what we're doing is, let's look at the best possible thing that we'll see down this branch. And if it's still not as good as what we've already found, let's stop looking. And that can have a lot of positive impact on your complexity. I guess not your complexity, but your time, your actual time in seconds. So we have an illustration of bounds here. Optimal exists, but we don't know what it is. So right now we're in an algorithm that searches for the lowest solution possible. We do know best so far. At some point we found a solution right here. This is the current path we're working on. There's a lot of different branches that we can take from this path. There's a possible one, possible, 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 possible. We're going to generate a lower bound on the remaining solutions from this current branch. We're going to say, in the best case, how good can this branch end up for us? And let's say this is our optimistic value. In this case, we don't prune. Optimistic is better than best so far. We might see a better solution later. We can't stop looking at this branch, so we're going to continue. Conversely, we might have an optimistic that's here. In this case, the best solution that we can think of is still not as good as best so far. prune this branch. Forget about this current path. Let the algorithm recurse back and check other paths, because this is a non-starter for us. Finally, we have this solution, or this case. Similarly, optimistic is better than best so far, so we're not going to prune it. But as you can see, there are no possible solutions that we'll end up finding. So it is doomed to fail, but we can't prune it yet. Now, these possible ranges are just a more broad illustration. Any questions on that? Good. Over pruning. This is what happens when you mess up. So our invariance to our bounds calculation is the upper bound, the best solution we have so far, has to be greater than or equal to the optimal solution overall. In other words, you've screwed up if you found a solution that is better than optimal. Generally, that doesn't happen unless you messed up. It's not hard to think about that as an issue. Maybe it might happen with a bug in your code, but you shouldn't find a solution that gives you a value better than the optimal solution. Doomed to fail. What do you mean doomed to fail, and how do we know that? By doomed to fail, I mean that it looks like at this point in time it might give us a good solution because our optimistic bound is better than the one we found so far. However, it doesn't have those solutions. We don't know that at this time. That's why we're saying we don't prune here, and there's a better solution, right? We actually have a possible solution here that's better than best so far. So not pruning it is not only correct, but it's also moving us towards a better solution. Here we prune because we know that there's definitely not going to be a better solution. We just forget about it. Here we don't prune because we think maybe, based on this optimistic solution, that we might find a better solution, a better best so far. However, it's doomed to fail. We don't know that yet, but it is doomed to fail in this example. The point of this like dichotomy here is to illustrate that you can't prune even if this thing will end up failing. Great. So back to the bounds. Upper bound greater than or equal to optimal solution overall. Let's not find an impossible solution that's better than optimal. More common is your lower bound must be less than or equal to the optimal solution for a given branch. The lower bound, you need to be as optimistic as possible. You can't have an optimistic solution that is not as good as the best possible solution you might find. The reasons for these invariants are the following. If our upper bound is invalid, we may never find a solution. Let me rephrase that. If we have an impossibly good upper bound that's better than the optimal solution, then we'll never be satisfied by an actual solution we find, right? Nothing will ever be good enough, so we just won't find a solution. Yes, for pruning, we only compare optimistic and best so far, because that's actually all we know. This is sort of like this is the omnipotent illustration, let's say. Like, this is you if you could know everything about the problem just to see what's actually happening under the hood, but at any given point in time you only know best so far, and you calculate optimistic. You don't know where all these possible solutions might end up, and you don't know what the optimal solution is, otherwise you wouldn't be doing anything. We're assuming we do not know optimal until we discover it through our algorithm. Yes, you don't know optimal until you're finished checking everything, right? because we have no idea what optimal might end up being until we check to make sure that that solution we found is actually better than everything else. I remember Dr. P's guide on P4. He uses optimistic and also uses the arms. I am not quite sure what that means. I'm going to continue. You can explain more if you want to maybe jog my memory. So if we have an upper bound that's too good, we will never find a solution. If our lower bound is invalid, we might accidentally prune the true optimal solution and our answer will be wrong. So if our lower bound, if our optimistic lower bound is actually worse than one of the possible solutions of the branch, then we might end up pruning it because we think that optimistic solution is not good enough. When in reality, we actually would have ended up with a better solution. So we need to make sure that both these invariants hold. Bounds tuning. There's a trade-off between tightness and performance. We have these trade-offs all the time in comp sci. So in this case, a tighter bound will allow for more pruning, so you'll prune branches faster, but calculating it will probably take more time. There's no perfect solution for these trade-offs. Different problems have different correct solutions. That's just the nature of these branch and bound problems. If the cost of computing our bounds uses more time than saved from pruning, the bounds are useless. That is always true and always important. And it's something good to remember. Don't get too caught up in this branch and bound algorithm. You need a way to quickly calculate bounds. Otherwise, you're not doing anything helpful. In the case of Project 4, an MST is a really quick way to find a lower bound on the remaining distance. So we're good. And that's why we can use it to eliminate a lot of the time that it takes to enumerate every possible path on TSP problem. If we didn't have an algorithm to quickly compute a lower bound on the remaining distance, then branch and bound would be a useless algorithm for this problem. So let's look at the whole pseudocode. You're going to say, if n fixed equals items dot size, then we've made it to a full permutation without pruning it. Process the items for the project. If not, then we have some not quite completed permutation that has an n fixed less than or equal to items dot size, or sorry, less than items dot size. So now we run our promising algorithm. We want to say, is it even possible for this to end up being a correct solution? And you're going to do that. You're going to do that with a combination of your current path and calculating the MST of the remaining nodes. Beyond that, we're going to continue to gen perms just normally. So keep calling gen perms with n fixed plus 1. Keep searching further and further down branches. Questions on branch and bound or gen perms or both of them together? Still confused on how swap and gen perms plus 1 works. Okay. So gen perms is written so that it's based on the number of n fixed plus 1. Gen perms is written so it's based on the number of fixed items you give it. So if I pass in an items vector of 100 items and I say n fixed equals 99, then it's not going to do anything. I'm going to say only permute this last one item. It's just going to be like, okay, here, it's permuted. If I give you gen perms and I say n fixed is 1, then the algorithm is going to take items and produce all the permutations running down the entire list, right? It does this using these last 4 lines. We have a bunch of unfixed items that live at the back of the vector, and we're going to run through each of these unfixed items swap it into the last position, and then call the same function but increment fixed. We're going to say, all right, we've fixed one more item, so try this. And we're going to do that for I equals n fixed to items.size. We're going to do that for every single unfixed item. So we're going to have our fixed group that we already passed in, and then we're going to have a function call to genperms with fixed plus a new fixed item for every new fixed item we could have. As we're running through that, we're going to swap that item back to make sure that we don't ruin further function calls. But we do this because what this algorithm is doing is saying, all right, choose one of the remaining unfixed items and fix it and call genperms again. It's just a way to continue to enumerate permutations that are going to grow in fixed size until they are items.size. When they're items.size, that's great. That's what we were looking for. And we're going to have n factorial situations where we get to items.size. Hopefully that was helpful. Great. All right, moving on to dynamic programming. Dynamic programming is hard, and it seems much harder than it is, and it just takes time to understand. I know the professors will recommend like LeetCode or just finding practice problems online, because it really does get easier the more you see it. You know, it took me longer than I took the class to understand it, because it just is something that people have trouble with the first time they see it. That said, I will try to take it slow, and let's try to learn it. Okay, dynamic programming. Remember the answer to every subproblem for overlapping subproblems. In practice, if you call a function 1,000 times and it always gives you the same answer, run it once and remember the answer. That's the crux of the strategy going into dynamic programming. We're trading time for memory. We're improving time at the cost of more memory usage. Usually the time improvement is huge and the memory usage is something you can deal with. Dynamic programming is very powerful. Let's see why with an example. Naive Fibonacci. Presumably you've all heard of the Fibonacci sequence, but Fibonacci sequence is created by summing up the past two numbers. So we'll start with 0, then 1. Then we get 0 plus 1 equals 1. Then we get 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 3 equals 5, and so on. This is some pretty easy code here. We're just having a normal naive recursive function. We've got two base cases. If n is 0, return 0. If n is 1, return 1. Otherwise, return fib of n minus 1 plus fib of n minus 2. If I then call this with 100, if I say fib of 100, you can imagine we're going to get a lot of function calls to fib. The runtime is 1.6 to the n approximately. This 1.6 is phi, is the golden ratio. That's a matter for a different class, but also very interesting. If we stick with a simple one like 6, you can still see that there's a bunch of recursive calls. Start with 6, 6 calls 5 and 4, 5 calls 4 and 3. We can already see we called 4 twice, and that's no good. If we go all the way down to the leaf nodes, obviously it only halts at the base cases. So we have 1, 0, 1, 1, 0, 1, 0, 1, 0. We just didn't have to do that. If we computed 0 and 1 once, then we'd like to just be able to remember it and use it in our calculations. So let's look first at bottom-up approaches. Bottom-up approaches are iterative approaches. We're going to start with our base cases, then we're going to build up some block in memory from those base cases, and then stop and return the value that you are trying to compute. Once you build it up to that value, then you can return it. Let's look at bottom-up Fibonacci. We first declare a vector to save the Fibonacci numbers, and it is n+1 size. We say fib 0 equals 0. In other words, the 0th Fibonacci sequence number is 0. Fibs 1 equals 1. And then we can just start computing. We just go from I equals 2 to I equals n and compute with the same function we had before. However, in this case, we're only computing every number once. So our runtime is now O of n, which is so much better. And then remember to call the correct number last. The correct number is the last number you compute. Top down maintains the recursive approach. So we're going to check if we already computed the value. If we did, return it. If not, calculate it, store it, and then return it. Let's look at top down. I think examples are very helpful for top down. We're going to start off by declaring this vector of remembered outside of the function. We don't want this to get redefined every time we call the function. Then we say, if we have enough space in this remembered function to calculate n, then we're fine, but otherwise we need to resize it, and we're resizing with -1s. This is important. By default, a number we haven't calculated will have a -1 in it. So next we say, have we ever calculated this number? In other words, is remembered sub n equal to 1 or not, or -1 or not? If it's not equal to -1, we already calculated and we can just return it. If it is equal to -1, then we're going to have to calculate it as a new result. We calculate recursively with function calls to fib. We remember that result. Very important. And then finally we return it. This is also O of n. And it's actually sometimes much more efficient than bottom down or bottom up, because we're only going to use the recursive function calls we need. So we might end up with a remembered vector that still has a bunch of -1s that we never needed. In the case of Fibonacci sequence, we won't have that because everything's calculated sequentially. But there are some problems, like the handwritten problem that you have today, actually, that might skip around a little and allow you to calculate fewer entries. Either way, I believe they always share the same complexity, time complexity. Questions about bottom up or top down before we move on to an example? Great. Positive subset sum. This is textbook DP problem that you'll get. This is a classic interview problem. A lot of DP problems look like this. Something about a subset of a group of integers, and you learn to recognize them, especially as you practice more. So you're given an array of numbers like the following, and this random array of numbers. Does some subset of this list sum up to exactly 104? In this case, yes, it does. 9, 15, 36, 44. Does some subset of this list sum up to exactly 106? No. Now the question is, how do we find that quickly? Before I keep going, I want to make a comment at the beginning of this problem. We don't care what the numbers are. The question that's being asked is, does some subset of this list sum up to exactly 104? That is a Boolean value. You're going to say that is true, some subset adds up to exactly 104, or that's false. Finding the exact numbers that sum up to it is a different problem. Okay, moving on. So here's our naive first idea. Let's generate every subset, add them up, and then check if it matches the number. So generating every subset, 2 to the n, and then for each of those 2 to the n subsets, add them up in O of n time. That's terrible. Really, really bad. So we can't do that. We need a new idea. We're going to use dynamic programming. If the array contains only small integers, then we can do this using DP. That first part means, I think it's probably, might be more accurate to say if the target number is 104 or 106, if the target number is small enough, then we can use DP efficiently. We can always try to use DP, and I don't think it matters so much about the array as it is the target. And you'll see that with the time complexity of the DP solution. So we need to make some recurrence relation. If the target is too big, would DP be slower? It's true to say that the bigger the target number is, the longer it takes to find the DP solution. And not only does it take longer, it takes more memory. Because what you're doing in DP is computing this memory's worth of solutions, iterative, or building it up. Whether it's iteratively or recursively, you're building up these solutions. So it's one thing to have really high time complexity, but if you need to do a subset sum and you're trying to sum to 10 million, then you're going to have a lot of memory for this DP solution. It's going to take really long. So we need to define some recurrence relation with base cases to decide how we're going to build the solution up. So let's do this. Let f of k comma x be true if some subset of a sub 0 to a sub k minus 1 adds up to x, where k is less than n. In plainer English, can we make x as a target number with just the first k numbers? We're not saying we need to use exactly the first k numbers. We're saying if we only had access to the first k numbers, does some subset of that comprise x? Can we make x out of some subset of that? If we can do that, there's two cases. Either we do it using a sub k minus 1, using the last item that we just added, or we can do it without using a sub k minus 1. Sorry for switching those. Or both. If we can do it with both, fine. So if we can do it without using a sub k minus 1, the set would count as a subset. Yeah, it's just subset, not proper subset. And the solution generalizes to that case. So it's not a problem, and we'll see that in the implementation. So if we can do this without using a sub k minus 1, then the same set is also a subset of a sub 0 to a sub k minus 2. If we can do it by using a sub k minus 1, then we need some subset from a sub 0 to a sub k minus 2 that adds to x minus a sub k minus 1. I'm going to wait a little bit on that and try to restate it. There's two options as we go from a sub 0 all the way to a sub n. As we keep adding more numbers we are allowed to use, we want to say, is it possible for me to make this number with this set? If it's true, it's either true because this new number was introduced, or because we could already do it. If we could already do it, then it was the case that we used to be able to make that number anyways. A sub 0 to a sub k minus 2 had some subset adding to x. However, if we have to use a sub k minus 1, then it's true that a sub 0 to a sub k minus 2 can add to x minus a sub k minus 1. Those are the two cases. So now we have this function built that helps us with the recurrence relation. We know our base case is empty has a sum of 0, so that's true. But empty where the sum is not 0 is always false. Now we want to know how to build f of k comma x. It's going to be some combination of factors of f of k minus 1, x minus 1, something like that. We're going to be using previously computed solutions, overlapping sub-problems, to build up towards our final destination. And this is what it looks like. F of k comma x is true if and only if f of k minus 1 comma x minus a sub k minus 1 is true, or f of k minus 1 comma x is true. So in plain English, we can make x with this group, this set k, or well, I guess the set up to a sub k, if either we can make x minus a sub k minus 1 prior, because then we would just add a sub k minus 1, or if we could already make x. If we could already make x, then we just already had a subset. This is all problem setup, and as you get better at dynamic programming, you'll recognize that this is a great case for it. These slides might help you work your way through what this question's asking and how dynamic programming helps. I'm going to leave them to you guys because they really get into the nitty-gritty, and it's probably better for you to work at your own pace on this. So let's make it to, at the very least, the naive recursive. So here is our overall function, subset sum 2. We have nums and target. So what we're saying when we call this is there a subset of nums that add to target? So now we make this recursive helper. The helper has 3 arguments. It has the integers, the nums. It has the target, but it also has k. It's the same k as we were talking about above. It's how many of nums are we allowed to use here? And we remember that this recurrence relation was built on that idea. So naively, if we don't use any DP, then we've just created a recursion problem. We have this base case if k equals 0, return target equals 0. In other words, it's only true if target equals 0. If target is less than 0, then false, because we're looking at positive subsets. Past that, we're going to say, what's the Boolean value of if we are using a sub k minus 1? That's a recursive call to can sum 2 with nums k minus 1 and target minus nums k minus 1, the last number. What's the Boolean value of leave, or if we're not using a sub k minus 1? And then we know that the answer is just take or leave. If either of those are true, then we're going to say true. If either of those are true, then we can build target with the first k numbers of nums. This will get you a solution. It's just going to take a really long time, because you might call can sum 2 on the same number hundreds of times. Here is our top-down adjusted version of that recursive function. We say that it's memoized. What that means is we made a memo. We are remembering our subproblem solutions. In this case, the memo is a vector of unordered maps, which is a little hard to wrap your head around. But you can imagine the axes are on one end, K. So, and then on the other end, we're working towards target, so 0 to target. And what you're going to do is you're going to start with 0, 0, where you have 0 numbers and you're trying to make 0. And you're going to work your way up. So you might have, okay, I have the first 2 numbers and I'm trying to make the number 3. We fill that whole number 3 row in and see all the different ways that we can make 3. Then we move to the next row, 4. We see all the different ways we can make 4 with the first 0, then first 1, then first 2, ... first K numbers. As that's built up, we'll eventually end up to the answer we're looking for, which is, can I build target with the first n numbers? Can I build target with all the numbers in some way? The index represents the target. Yes, the vector indices is the target. Or sorry, it appears that the vector indices are K. But one of the indices is target. So this is a 2D map, and we're indexing not only for the number of nums that we're allowed to use, but we're also iteratively building towards that target sum. What does memo represent? Memo is that 2D. It's that 2D memory that I'm talking about. You could use a vector of vectors, which is more, or it's easier to understand, but not as good of a solution. The key of the map is the target. Yeah. So I think that in this case, the key of the map will get you to the entry for the actual number we're summing to. And this is top down, so we're still going to be using recursion. So we're going to define this memo, we're going to pass it in. This is the broad function. Sorry. This is the broad function, subset sum2. In subset sum2, we're going to start off defining this memo. We're going to make it nums.size plus 1. In other words, we're going to have an unordered map from ints to bools for every item, for every num. And then we're going to pass that memo in along with our old arguments. We're going to have the same base cases, but then we're going to have this check. We're going to say if memo sub k dot count target, return memo sub k target. What that means is if we've already computed this in the memo, then we can just return it. If not, we need to recursively call for take and for leave. We need to compute answer equals take or leave the same way. And then we remember to store that result so that we're improving our efficiency at memo sub k sub target. Then we can return answer. This runtime is O of target times num.size, which is kind of crazy. It doesn't really make sense that, it might not remind you of anything, the fact that you're iterating over like a target integer. But that's what we're doing. We're building up. We want to see if we can make 0, and then we want to see if we can make 1, 2, 3 out of these subsets. And we can build that way until our target integer, which could be like something random, like 79. And then we'll just have a 79 size, or one of the axes will be 79 size. But That's how a lot of these subset problems work. That's how a lot of DP problems work, actually. This runtime will make more sense in bottom up. I'm going to leave you to these as well. Here's the bottom up code. In bottom up, we're going to use a vector of vectors. In bottom up, we're going to say, let's initialize this 2D table. Can you re-explain the AK minus 1 versus A sub k minus 1 versus AK? Okay. So maybe it'll help for me to just run through and explain what the K's are for. So K, when it's passed into can sum to, is the number of elements you're allowed to use. So in this case, when we're calculating for K, we're saying, all right, K has been introduced, like A sub K. So our answer here depends on the answers of K minus 1, the answers of the subset without A sub K. If we're going to use A sub K minus 1, then we need to check if that subset could have computed target minus nums K minus 1. In other words, let's see if we can make the difference up so we can use the rest of that subset. We also check if we can make this target without A sub K minus 1, which is the same as just saying, all right, what was K minus 1 with the same target? What is memo sub K dot count target? Dot count returns either 1 or 0, depending on if the key is in the unordered map. It's similar to dot find. So this is the same. I think this is exactly the same as saying if memo dot find K does not equal memo dot end. Also, I don't understand why we need a vector of unordered maps. Wouldn't an unordered map be enough? No, because this is a two-dimensional buildup. So we're actually not only computing down K, we're not only saying we can use no elements, then 1 element, then 2 elements, all the way up to n elements. We're doing that for every number from 0 to target. We're going to start off and say, can I compute the number 0 with all of these elements, 1 element, then 2 elements, then all the way to n elements. And then once you have those answers, those are going to be helpful when computing if you can make 1 and 2 and so on. When you're checking to see if you can compute the number 38, then what you're going to say is, for each of these numbers, could I compute 38 last time? And also, could I compute 38 minus the current number last time? What is the size of the vector? In this case, the size of the vector is num size plus 1. So yes, K is the same axis as that, yes. But the full vector is going to be enough to fit all the elements, right? Because at the end of the day, we want to end up where K equals nums dot size, right? K is not always equal to nums dot size in these recursive calls, because you need to build up to where K equals nums dot size. In other words, computing for a given target, for computing the answer for a given target for the full set, you need to first compute the subset with just 1 element, and then the subset with the first 2 elements, and then the first 3 elements. And you're going to use each overlapping subproblem to build up to understand the answer where K equals nums dot size. Yes, on one axis, you keep going until k equals size. I think that the bottom-up implementation of this will help you understand this problem much more. So in this case, remember what bottom-up does. Bottom-up is going to work iteratively. So we're going to say, I know how much we need to calculate. We need to calculate a table full of bools, a 2D vector that has an axis target plus 1 and an axis nums.size plus 1. So let's just start off and create this whole table. And then we're going to go through and fill it in. We're going to start at the very first entry, and we're going to fill it in all the way down until we have table sub target sub nums.size here. That's the return value. So once we initialize this table, we're just going to have a double for loop. We're going to say for targets, for k's. Check if the base case holds. If it doesn't hold, then we need to do that whole take or leave. So we need to say table sub t sub k equals table sub t sub k minus 1, or table sub t minus nums k minus 1 sub k minus 1. It's the same recurrence relation, but we're just building it bottom up. We're starting with the simplest cases and moving towards the case we're looking for. Once these for loops are done executing, the last thing we calculated was table sub target sub nums.size, so we return that. Here we can see much more clearly that the runtime is target times num.size, because the majority of the code is just this double for loop that runs target times num.size times. Take a solid minute to process that, because dynamic programming itself is hard. Subset problems can be hard to pick up. If anyone thinks of any questions, you can hit me with them. But I think looking at this pseudocode it's just normal code. Looking at this code for a long time, you can start to see where this comes from, as long as you understand the recurrence relation of the problem. Is bottom up usually iterative and top down usually recursive, or does it depend on the specific problem? To Neil's question, yes. Definitely usually, I believe that is just the definition. Bottom up, every bottom up I've seen is iterative, where you define the whole vector, 1D or 2D, whatever it may be, and then you fill it in from the bottom up. And then top down is the recursive, where you'll ask the function for the final answer, and then the recursive stack frames compute and remember. How is the or portion determined in the else statement? The or portion is part of the recurrence relation. So let's go up back where we were talking about this stuff. Right here is where the or statement comes in. It's actually right here. So it's based on the problem. Every problem is different. That is half of solving the DP problem, is just understanding how you can build on subproblems. So in this case, we found a base case, and then we realized that you can define this subset problem as a function of two prior calculated values. And if either of them are true, then this is true. In other words, if we can make this subset with or without a sub k minus 1, then we should say true to this. Let me get back to the problem, or the, okay. Why do we return the table at nums.size again? Is it because it's the last thing you put into the table? Really it's because that's what the problem asked for. So the table at nums.size is where k equals nums.size. In other words, it's where we're allowing ourselves now to use every single one of the nums. And the problem statement was, can you take all of these nums and use some subset to make this target? So we need to use k less than nums sometimes so that we can build the table. But at the end of the day, we're still computing all those subproblems as an effort to find this number exactly. Because this number means, is it true or false? Remember bools. Is it true or false that we can make this number with all of the numbers in nums? I'll let you guys look at this for 15 more seconds. Hopefully it's starting to make sense. And LeetCode is definitely your friend. Okay. Let me introduce the handwritten problem then. The handwritten, this is, I would say, the most famous DP problem, especially as you are beginners to DP and start learning things, is the knapsack problem, O1 knapsack, as described in lecture. Try not to copy it from the slides, try and build it up yourself. You remember the problem, you have a bag of weight capacity cap and a group of n items, each of which has a value and a weight. We give you a value vector and a weight vector, where value sub I is the value of the ith item and weight sub I is the weight of the ith item. Your goal is to choose which items to put in your bag so that you maximize the combined value of all the items without going over the weight capacity. In other words, you're looking for the group of items that give you the best possible value given the capacity you have for weight. Important to note, just like last problem, this is a common mistake that leads to confusion. You are returning the maximum value. You're returning the value that you can find. We don't care how you got it. You don't have to remember which items led you there. They need to be possible, so your algorithm needs to consider items as it goes on, but that's not something you're remembering. What you're remembering in each entry is your maximum weight so far. So you're trying to find the maximum value under the constraint of the weight? Correct. That's exactly correct. And a relatively succinct way to say it. We ask you to return the maximum value of the items under the constraint of the weight of the items. Cap is the maximum weight. The reason it's called knapsack is because the problem statement is usually you have a knapsack, which means backpack. You have a backpack with a capacity of 50, and here you have items with values and weights. What are you going to put in your backpack? That's your handwritten. Handwritten is up on Gradescope. You also have AutoGrader and Quiz for Lab 10. The AutoGrader is a DP problem also. I think it's called Deals on Meals. There should be a section in there about returning negative 281. The AutoGrader for Lab 10 has kind of a little Easter egg. If you pass in a .cpp file, but all you do in the function is return negative 281, then you'll get this really handy blurb about how to do the problem. It'll walk you through it. You don't have to stress out too much over it because it is a hard problem, and DP starts out a little confusing. Any questions on handwritten or the AutoGrader or the midterm or anything else in general? I'll stick around for a while if anyone thinks of anything, but that's all I have. Good luck on project 4. Good luck on lab 10. Good luck studying for the final. Yes, to get the hint, just I forget what the actual function that you're supposed to be implementing is. It might be called deals. I think you're supposed to do that from the function though. Definitely read over the spec for the lab. I know we were talking about making it very clear. It should be one of the first things in the spec, although I haven't looked at it, so don't quote me on that. If you don't find anything on it, put up a Piazza post. Someone will get to it.